Welcome to the Fractional Calculus Seminar Series. Today we have Dr. Edmond Zhou, who has received his BS in Physics from Peking University in China, where he worked on statistical physics of star formation. He then pursued his PhD in physics at MIT, where his thesis focused on material sustainability by understanding how phase transition in porous colloidal media, such as cements or batteries, lead to material degradation. Currently, he is a Dinkwood postdoc fellow at the California Institute of Technology, where he combines statistical physics and fluid mechanics to study fundamentals of living matter and its application in biomedical and responsive materials. We are very happy to have you here. You may please begin your talk.
Yeah, thank you. Thank you, Pavan. For the kind invitation and introduction. And hello, everyone. It's my honor to join the seminar series here and tell you today about my recent work on some work on fractional calculus and which is part of a bigger project that eventually lead us to a design for anti-infection catheters. Okay, so I will start with a bit of background about active matter. As you probably have heard from other speakers, active matter is a relatively new field in statistical physics, and it's basically motivated by the all kinds of phenomena and interesting behaviors, collective behaviors in biology. So people start to think about more abstract ways to model these systems. So basically, you can consider anything that converts chemical or internal energy into motion or mechanical force. You can think of that as an active matter, right? And of course, we experience these systems in our everyday life, such as the bacteria or these bird flocks, and within our body cells, or at some level, we can also model humans as active matter. And these systems are intrinsically non-equilibrium, right? Because they have a driving force from inside these agents, and and that means we need to have a new frameworks in statistical physics to understand these systems, and it happens to be a very interdisciplinary field so far. Basically, a lot of researchers from the background of statistical physics, fluid mechanics, applied mathematics, and chemical or mechanical engineering, they all have their own reasons to get interested in these problems. Today, hopefully, you will see that my work here is part of this change, and where we think there are something very interesting and useful at the same time to at the intersection between active matter and applied mathematics, especially fractional calculus. So what brings us to become interested in studying these systems? There are a lot of reasons. For example, can we learn from these collective behaviors of these army ants or the fish schools? And can we learn from them to find better ways to design swarming robots, right? Or can we understand how our body cells heal a wound and try to transfer that knowledge to make some self-healing materials? Or on the other hand, we know these systems, they also interact with the environment through all kinds of rich interactions. And a lot of times they interact through the fluid phase, right? So if we can understand better how they interplay with the environment, maybe that will help us to find a lot of real engineering solutions to a lot of real application problems, such as the catheter problem that we're going to talk about today. Okay. let's talk about first some very basic models in active matter. So I would consider these two are the the simplest models for to model active matter, right? On the left, you're looking at so-called active Brownian particles. So an active Brownian particle is simply a sphere that propels itself along a direction q at a constant velocity u naught, right? And the direction q is diffusing over time a characteristic timescale tau r, right? And we can write down the transport equations for its probability distribution, and then we can model that. We can do simulations to find out its typical trajectories, like the one showing here. Um, and on the right side, you're looking at so-called run and tumble particles. So it's very similar concept, but the only difference is this model is discrete. It's not a continuous model. So the run and tumble particle will go in a straight line segment for again, a certain time tau, and then it will suddenly randomize its orientation, right? So it suddenly choose another direction and go in that direction for another time. And we can characterize the correlation time by this waiting time distribution. And specifically for the run tumble particles, we're going to use a exponential distribution for that. And as you can imagine, although these two models, they are different at the microscopic level, but at the macroscopic level, the long time behavior, both of them are going to converge to Gaussian behavior. So here for the run tumble particles, the waiting time distribution, we explicitly specify that to be an exponential distribution, right? So it's very straightforward to see. And I'm going to quickly show you that active Brownian particles also have exponential correlated time. So here is one way to see that, right? So basically, when we specify the dynamics of the active Brownian particles, we are essentially introducing a Gaussian white noise as a torque that rotates the velocity vector, right? So this is essentially the underlying dynamics can be described by this equation. And here the C is a typical Gaussian white noise that we are familiar with, which means that the order odd order moments are going to be zero as the ensemble average, while the even order moments are going to follow Wick's theorem and decompose down to the second moment, right? So now we just do a very straightforward calculation of the velocity autocorrelation function, and then we apply the Wick theorem, and then at the end of the day, everything sums out very nicely to a exponential correlation, right? So that shows you that the active Brownian particles also has exponential correlation time, just as the same case as the run and tumble particles. But run and tumble particles, we explicitly specify that. So both of them are on the large scales. Both of them behave like a kind of like a Markovian system, and then they are going to converge to Gaussian diffusion behavior. So now I'm going to switch a bit and introduce the main character of today's talk of mine, which is a medical problem. So the problem is called catheter-associated urinary tract infections. Okay, so if you have visited the hospital and see some patients who are immobilized and they can only stay on the bed, then it's very likely you're going to see some of them have a urinary catheter inserted into the urinary tract, like the picture schematic here. So that's a catheter coming all the way into the patient's bladder. So of course, the purpose of the catheter is to drain the urine from this immobilized patient to outside the body and all the way into the urine bag. And however, these catheters actually are known to cause a lot of infection problems. Okay, the urine. So if the patient has a healthy kidney, then actually the urine of the patient is always sterile, so there's no bacteria inside. But because of the catheter in the urinary tract, bacteria can actually transport somehow from the outside world into the body of the patient and infect them. All right, and this is a quite serious problem actually, and it's a global-wise problem. So no matter where you look at on the map, uh, basically it happens in almost every country, and the infection rates of these catheterized patients are pretty high. And here are some data from the United States, where as you can see, it caused a lot of death, and the economic impact is also humongous. So it's a big issue. What are the current methods to uh, make to solve this issue? So the mainly what people have been practicing in the hospitals is to try to replace the catheters more frequently. So, for example, typically if the catheter stays inside the body of the patient for about a month, then almost 100% that patient is going to be infected. So typically in the hospital right now, people try to replace these catheters every 2 or 3 weeks at least, and that has proven to be the most effective so far, right? However, we cannot push this we can only push it to a certain limit. First of all, these catheters, there's material cost to that, and also you need nurses' labor to do it, right? And we are always in shortage of nursing power. And besides, if we replace the catheters too much, that by itself is quite a painful experience for the patient, and it also can cause mechanical damage to the patient's urinary tract. So we cannot do that too often. And the other thing we can do is to impose stricter nursing procedures. For example, try to disinfect and wipe these catheters as much as possible. But that's kind of what they're already doing, right? So it's not getting rid of the problem completely. So, what about from a engineering perspective? So can we use some special materials or devices to prevent that? Actually, people have thought a lot about this direction, and there are a lot of work done on the so-called antimicrobial coatings. However, these coatings typically they are designed to be to detach the bacteria so that they can prevent biofilm formation. But they are not particularly effective in terms of preventing the catheter infection, which we have some idea why. And as I'm going to tell you about our understanding of the mechanism for these infections. So what is the possible mechanism for these catheter-associated infections? The first idea coming to mind is maybe the bacteria from the air falls onto the exterior surface of these catheters, and then they just walk along the way into the body of the patient. However, that's very unlikely because, as we just mentioned, our nurses are trying to do their best and they disinfect these catheters very frequently. And the outside of the catheter is usually kept dry, so it's very difficult for bacteria to go into your body through that way, according to many doctors that we consulted, right? So what about the other possibility, which is going through the interior of the catheters? If but in the conventional understanding, if we only have passive dust particles, let's say, then it's also impossible because, as we could imagine, inside the catheter, you have more or less a per se flow, right? But that flow is always going from inside the body to the outside, and past the dust particles can only be washed downstream. So they don't have any chance to go back to your body. So the convection always dominates over the diffusion, right? However, if we have active swimmers like bacteria, there is unexpected behavior, which is so-called upstream swimming. Okay, so the simplest explanation for this mechanism, which doesn't require more details of the hydrodynamic interactions of the bacteria, is that we can simply imagine the bacteria again as just a sphere, right? But now let's say this bacteria is trying to go across the catheter, so it's trying to go towards the upper wall here. But as we know, the Poisson flow has a shear or vorticity, right? And in the upper half of this channel, the vorticity is rotating counterclockwise, which means as even if the bacteria is not turning by itself, its head direction is going to be turned. Sorry, it keeps doing that. The head direction is going to be turned towards the upstream direction, and when it lands on the upper side wall, the head is more likely, statistically speaking, be pointing up. And that's where the Poisson flow is very slow due to viscosity with the wall. So the bacteria is going to just walk along the wall towards the upstream direction for a while before it turns the direction again. And then, so a persistent bacteria can perform this zigzag kind of trajectory and to go all the way upstream, even though the urine flow is always pushing out. This phenomenon has been known for around for a while, and people actually have recently done very detailed microfluidics experiment to observe that. So, for example, in the experiments I'm showing here from Eric Clement's group, um, what they are doing is they put a reservoir of E. coli down here. That's a reservoir, and then the top of the reservoir they connect to a very long and thin microfluidic channel, and then inside the channel they're pumping fluids from top towards the bottom into the reservoir, right? But as you can see, this is what they observe under the microscope. So this video on the right is a image tracking of the bacteria they are observing. And as you can see, indeed, the bacteria are actually going along the wall towards the upstream direction. And sometimes they get washed down in the middle, but then they do that again. So that seems to be a real mechanism. Okay. Um, and what's more is that they not only observe the phenomena qualitatively, but they can also try to measure the distribution of the bacteria inside this channel quantitatively. So when they did that, it's actually quite surprising. What you're seeing here is because the channel is so long, they chop it up into 4 segments, right? And then they lay them in parallel. So as you can see, all the way up to almost the very upstream end of this channel, you can still see the fluorescence from the bacteria. And this is within about maybe 10 minutes. So uh, some of these bacteria, they travel really, really long distance, okay? And that's going to be a surprise if you think these bacteria as the active Brownian particles or the run and tumble particles that we just mentioned, right? Because for them, the long time behavior is always Gaussian. So I would expect something more or less of a Gaussian feature. But here they can travel really long. And here on the bottom, this is their measurement. So of the distribution of the bacteria. So after averaging, you can see that it basically shows up a parallel tail, right? So that gives us the hint that these bacteria, they might not be doing Gaussian type of motion, but the underlying mechanism might be more related to Levy walks. So that's our motivation to start thinking about how to model these bacteria properly to capture that super contamination behavior, right? So we're going to move from the Brownian walk or active Brownian walks on the right towards the left side, which is a Levy walk or Levy flights. And we're going to name this model as naturally as active Levy swimmers. So before we jump into the math that we did, first I would like to discuss very briefly some potential mechanisms that leads to these behavior, right? So mainly there are two things that we are aware of. So the first one, of course, is from the biochemistry of these bacteria, because a lot of recent studies have shown that the metabolic system is very complicated, and the reaction noise actually shows some parallel distribution. So that's likely a mechanism that drives bacteria motion to be also parallel. And also, it could come from the environment, the fluid mechanics, right? And recently, people have also considered basically from simulation and theory, they look at the hydrodynamic interaction in these low Reynolds number flows, and because the hydrodynamics here is long range correlated as the Green's function decays as also algebraically. So they realize even if you put a Gaussian tracer into a fluid with some other particles moving around, that can lead to parallel in the dynamics of the tracer as well. But we don't know for sure which one, or maybe both, or maybe some other mechanism is the real reason. So this is currently still an open research topic. Nevertheless, we know the phenomenologically that these bacteria, they perform very, very long correlated walks. So we're going to try to model that as a Levy process. So here we are trying to be very careful and avoid some, try to make the details work. So we're going to particularly choose the model to be Levy walks instead of Levy flights, right? Because although I think probably in the mathematics literature, people are more familiar with Levy flights, but there is a small issue with that physically, because in this model, the particles are just jumping around with arbitrary velocity, right? So, and it's also technically difficult to deal with the boundaries and interactions. So we do not want that, but instead we want the particles to be moving with a constant or finite velocity before it changes direction. So basically, we are going to modify the run and tumble particles model. So everything is similar to the run and tumble particles, except now we change the waiting time distribution. So for the run tumble particle, the waiting time distribution is exponential, right? But here, for the Levy swimmers, we're going to use a Pareto distribution, which has a parallel tail to model the waiting time, right? And with that waiting time distribution, we can write down the propagator for this Levy swimmer. So basically, the Levy swimmer, again, is going to run for a parallel distributed waiting time in the one direction, and then it's going to turn the direction randomly and then go in the other direction for another certain time of tau. And since we're talking about bacterial motion inside a catheter, which is a finite confined space, right? We're going to need a proper boundary condition. So what we observe in real experiments is that the bacteria, once they hit the walls, they're going to slide. They're going to basically just move along the wall. So we're going to impose a sliding boundary condition. And our general goal here, in terms of mathematics, is to derive the equation and find the steady-state solutions for these Levy swimmers. Okay, so let's start with some easy, like low-hanging fruits, like easy analysis. So let's think about just simple run tumble behavior in 1D channel, right? So it's the bacteria is running on this 1D line along the x-axis, which is bounded by two endpoints at XL and XR. Now we have basically just two parameters. One is both of them to parameterize the Pareto distribution. So one is the minimum runtime, and then the other one, more important one, is the power law index, right? And in let's first consider the limits of strong confinement. The strong confinement is in the sense that the bacteria, they actually do not turn around much in the bulk, right? So their run length, typical run length, is much longer than the channel width. So in this case, because they never have a chance to turn direction in the bulk, they basically just move ballistically from one end to the other, right? And then they stay at the end point for a while, and before they turn the direction and go to the other wall, right? So this, in general, this will lead to a singular wall accumulation. So if we consider the probability density of these bacteria, we will have basically two delta functions at the endpoints, right? And in the middle, things are just smooth, flat. So what's the only interesting quantity here would be the fraction of the particles that accumulate at the endpoints or on the walls, right? And that's very easy to estimate. Essentially, we can consider how much time the bacteria is going to spend in the middle versus how much time on the walls, and that will give you this estimate. And then if we know what's the swimming force or the force for self-propulsion, then we can work out what is the physical force or pressure on each wall. And then if we go to the other limits of weak confinement, then the bacteria is spending a lot of time in the middle before they really see the boundary, right? And we anticipate in this case, you can approximate the motion by a 1D fractional diffusion. So we're going to formalize this idea. So let's consider some general considerations for 2D round tumble particles, right? So we can start from a kinetic equation where we consider probability distribution in both space-time, but now also in terms of the orientation Q and survival time tau. So tau is the time that it has been going in this direction without turning, right? And if we do that, then you can write down the kinetic equation, which is a famous equation. And here, here the beta of tau is related to the turning rate, and you can derive that from the waiting time distribution. So if you have exponential distribution of the waiting time, then beta is a constant, while for our Levy swimmers, beta is a power law 1 over tau, basically. So now the question we want to answer is what is the long time limit of that? And that's there is a classical framework to renormalize these equations to arrive at the so-called hydrodynamic equations where we don't really know the orientation and the survival time. So that's so-called Hilbert expansion technique. if we apply that to the run and tumble particles with exponential runtime, basically we try to get rid of the tau and q variables, right? Then at the end, we're going to arrive at such an equation, and because of the exponential correlation time, this extra term is going to vanish, and we get a intermediate equation with a right-hand side related to the turning. So we're going to call it the turning operator. And at this point, we can apply the Hilbert expansion technique, where we anticipate that there are two separated timescales, right? So one is a diffusion timescale, the other is a advection timescale, and they separate in scales. And if you do that expansion, at the end of the day, when we get rid of the Q, then in space-time variables, we go back to the diffusion equation very nicely. Also, actually, for the run and tumble particle, just a small remark. You can actually analytically get a solution for it, but only in the Fourier Laplace space. So technically, in principle, if we can conduct the inverse transform, then we actually can write down the distribution. So now, what about our Levy swimmers? So in principle, we can apply the same Hilbert expansion technique, but now two things are different, right? So basically, we have power law distributed waiting time, and we have boundaries. So formally, this Hilbert expansion can proceed very similarly to the round tumble particles, and basically we first do a Fourier transform, and we get rid of we transform the differential operators into just scalars in K-space, right? And then you do the Hilbert expansion with these scalars, and then inverse Fourier transform back to get the fractional diffusion equation. And people have conducted these expansions for us. So only things we need to be a little careful is these two small technical details. So when we do the Fourier transform, now we have a finite domain, so we have to restrict the density to be zero outside of the domain, right? But the rest of the Fourier transform just proceeds as usual. And now, if we're trying to assume the power law scaling, that means we really are thinking about the weak confinement limit, where in the bulk you do have the power law scaling, right? So as long as we're careful about this, then we can safely repeat the Hilbert expansion procedure, and then we know from this procedure we can see naturally that this fractional heat equation, the fractional operator will hold with the Rees definition. Okay, so now let's try to solve a simple problem where we have 2D Levy swimmers confined in this 2D channel, and we ask what is the steady state distribution of these Levy swimmers, right? So now we, of course, intuitively we should have a separation of variables, and we can reduce the problem into a 1D problem. So we're going to formalize this idea. Let's start with this fractional heat equation, and then we can go into the Fourier space, and then in the Fourier space, now we can apply the restriction of the domain and then inverse Fourier transform back. And this time, we do see that we have a separation of variables and a 1D problem. So now to determine the solution, we also need a proper boundary condition. And there are actually many possibilities for Levy processes, right? Such as we can have the specular reflection or the stopped behavior or a reverse reflection and so on. but we don't want any of these. As we mentioned, the real physical boundary condition for the bacteria should be a sliding boundary condition, right? So when the bacteria hits the wall, it's going to slide along the wall. Although this is microscopically, it's trickier, but for our problem where we're dealing with the macroscopic fractional diffusion equation, that's actually simpler, right? Because that just corresponds to a zero flux boundary condition. Okay. So now we impose this zero flux boundary condition. How do we translate into the mathematics? So basically, in general, we can write down the Riemann-Liouville flux in this form with a fractional derivative operator. And in our case, because of the left-right symmetry across the channel, this Riemann-Liouville flux will reduce to a Ries flux, right? So it's a symmetric flux. And we know how to write that, and we can define it, construct it from the one-sided Riemann-Liouville derivatives. So now at steady state, with the zero flux, essentially we're just saying that the flux should be zero everywhere, right? So that further simplifies the equation. So now we just have this fractional derivative operator applied to the density, and that should be zero. So people actually know the general solution to this equation by Kelly and his coworkers. And in our case, again, by symmetry, the Ries flux should vanish at both boundaries. So with that additional constraint, we can get rid of the one of these terms. So we are left with only one of them. And this will be our steady state solution. And one thing to remark here is also that the only parameter here, alpha, is the same for the microphysics. So alpha is the power law index for the waiting time distribution of the bacteria, right? But then all the way carried out here into the fractional PDE, and eventually the final form of the steady state distribution. So that's something pretty nice. And here the C naught is just a normalization constant to determined by the total density of the bacteria. So it's nice to get a steady state distribution, but this steady state distribution is not homogeneous distribution. It's not a constant, right? So maybe this is maybe this obvious for mathematicians who are familiar with fractional calculus, but in other fields like engineering, actually, historically, these fractional operators has been somewhat confusing in the literature, right? Because people were worried about, if you use a Ries derivative, you can come up with these non-constant steady-state distribution, and that's very counterintuitive to traditionally. So, for example, a lot of people actually criticize the use of the Ries operator in their work. But now, for us in this problem, we are actually very happy with it, and we're comfortable with a non-constant steady-state distribution. And that's because we have active Levy swimmers, and they are actin matter, so they are intrinsically out of equilibrium. So anything can really happen, right? So it's not going to be a real surprise, but we can conceptually we can accept that. Okay, so since we have the analytical form for the steady state density, we can try to compare that to our numerics. So we did some numerical simulation for such 2D Levy swimmers, and we can change the mean waiting time the mean of the waiting time distribution, right? And as we change that tau r, the fraction of the swimmers accumulated on a wall is also going to change accordingly, right? And also, as we change that mean runtime to larger and larger, to smaller and smaller, then we're going to eventually converge to the weak confinement limits that we have been focusing on, right? And that's these darker dots are the simulation results, and the black dash line is the analytical solution for that, which will be in the limits of infinitely weak confinement, right? And of course, in the simulation, we can never really get to that, but as you can see, the curves progressively approach the analytical solution. Also, we can recover the density profile for round tumble particles, right? So again, as you can see here, for the round tumble particles, the characteristic feature is that you always have a constant density in the bulk, but you're going to have a boundary layer, and the boundary layer thickness is related to the average runtime. So if we, in the Levy swimmer model, if we increase the alpha power law index to above 2, right, then the process becomes Gaussian process again. So then we should recover the run tumble behavior. And indeed, we did that. And as you can see, if we make alpha equals 3, then again, we recover the constant bulk, but with a boundary layer. Okay, so it's all good. And one of the things we did is a kind of a sanity check to know the numerics is correct, is that we can also confirm the fraction of particles on the wall in the strong confinement limit, which we worked out as the simple analysis before deriving the fractional equation, right? So we know that for the strong confinement limit, and that's plotted here as the black dash line. And then we did simulations with different alpha values. And as you can see, as we would expect, they all collapse onto the black dash line in the limit of strong confinement. So this is reassuring. Okay, so that's the mathematics that we did for this problem. So now we have done some mathematics. We still want to go back to the real problem, which is the supercontamination of the bacteria and infections through the urinary catheters. So can we solve this problem in some way? So we actually come up with a very simple design for the interior geometry of the catheters, right? So we put some obstacles on the walls of the catheter, and these obstacles, they are tilted towards the downstream direction, and we hope that this will cut off the power law distributed runtime along the wall of the bacteria and redirect them back into the middle of the positive flow so that they get washed downstream. And here is a simulation. As you can see, this Levy swimmer initially performs that zigzag behavior, and it tries to go along the wall upstream as we expected. But then, yes, eventually it gets redirected back into the middle and washed downstream. And we can try to optimize the geometry, right? So we use some machine learning technique to accelerate the pipeline and find a good geometry. And I was quite excited, so I tried to see this in a real experiment. And for me, it's a very exciting and novel experience because I'm trained as a theorist, so I never done experiment before this one. So I was really happy, and this is a photo of myself in the clean room where I was trying to do photolithography to manufacture these microfluidic channels. So this is my experiment. So I made a microfluidic channel like that, like the design we showed here. And as you can see, I highlighted two bacteria So as you can see, they try to go upstream along the wall, and then yes, they got redirected by the obstacle and eventually back to the middle and then washed downstream. So that seemed to work. And we want to see if this can also work for a real size catheter. So I 3D printed catheters of our design. So these are real size catheters. These tubes have a diameter of 1.6 centimeters, and they are 8 centimeters long. So we connect the downstream end of the tube into a bacterial E. coli reservoir and upstream end to a syringe pump. And we're going to pump just water into the through the catheter downward into the bacterial reservoir. And then after some time, we're going to cut these catheter into segments and then measure the distribution of the bacteria that way. So at the end of the day, we see that our design seems to be really effective. So if we compare the upstream amount of bacteria, then we see actually a 100fold suppression of the amount of bacteria upstream. So that seems to be really working, and we're pretty happy about it. And we filed some patents, and now currently we're fundraising for clinical trial. So hopefully one day these catheters can really help the patients. Okay, so just some final remarks before I finish. So this is a quote from the Caltech News on our catheter experiments, which I really like. I think that's what I want to do for my scientific career. Basically, we want to go all the way from theory to simulation and experiments to make some real world impacts, right? But also, specifically for us here, I think this is a good example of where the applied mathematics of fractional or the calculus can be useful, right? And I believe this is only one of the examples in the field of active matter, because a lot of biology, we know that there are a lot of Levy walks and fractional order behavior in biology. So I think there are a lot of more opportunities to do something similar. So, and I look forward to that. And this is my teammates, my colleagues, and I couldn't have done any of this without them. So yeah, thank you. And if you have
Thanks,
questions, yeah.
thanks, Edmund. That was actually a very nice talk. For
Thank you.
questions, please raise your hands. I'll call out your name in the order they appear on my screen. Equally, you can unmute your mic and go ahead. Okay, I don't see any raised hands. I just have a little curiosity to ask. Okay, you are looking at fractional waiting times, and then I saw that the operator that you were defining was in space. So how did you do that? So in the first part of the talk, you were talking about fractional waiting times. I mean, Pareto. Okay, this one.
Right, right. Yeah, that's a good question. So I think all the tricks and I mean all the reasons are really in this procedure of the multi-scale expansion, right? So as you mentioned, um, we do start from a parallel distribution of the waiting time. But then what we did is we followed this Hilbert expansion, which is really a multi-scale series expansion, right? And when you do this multi-scale series expansion, you're going to say, I have some separation of time scales, right? And And that's where the power law distribution of the waiting time comes into play. So here, because of the power law distribution of the waiting time, uh, we cannot assume a integer order of the series. So now when we write down the series expansion, I cannot write a integer order series, right? So I have to write a fractional order of series. So that's where the power law nature of the waiting time comes into the math. And then if you write here instead of just k integers, but now you write the fractional you write the fractional numbers there from the alpha of the waiting time, and then you do the multi-scale analysis. Uh, at the end of the day, it will appear it will basically change the power law in the index in the Fourier space of the k, right? So now they come into the power law of the k, and then we inverse Fourier transform back. It becomes a fractional operator in space. So yes, there is a step going from the time to space variable, right?
Okay, one quick question about that. Hilbert's in the previous slide.
Yes.
So are those pk numbers over there like coefficients or something, or what is pk?
Oh, so this is so P is the probability distribution, so the intermediate one. So this P is a function of both space and time, which I put a dot here, and also the orientation Q. So, but now we want to get rid of the Q. The whole point of doing this multi-scale analysis is that because in experiments, it's very difficult to measure Q, right? So we don't
Mm-hmm.
know Q. We typically know the space-time distribution, right? So
Mm-hmm.
now we want to get rid of the Q, and that's why we do this multi-scale expansion. And yeah, so
No, but in this Hilbert expansion, you have sum of pk to the epsilon to the power k. So what is that pk is my question.
I see.
Pk.
So, actually, I need to look up the more details in the paper we wrote, but I think PK is just so here these PKs are the different orders, and these PKs are only functions of space-time, if I'm correct. Okay,
Mm-hmm.
so basically we're trying to expand. We're trying to get rid of the Q, so we keep the space-time x and t, and these PKs are those are functions of only those variables. So at the end of the day, what you get is actually the what we write down is really the leading order equation, right? So in the case for the normal Gaussian behavior, the leading order equation is, as you can see, is here. Is for the P naught, right? So uh, yeah, so the leading order equation is the P0, and then you actually in theory you also have all the higher order equations, right?
In the next slide, you had the alpha to minus, no, no, oh yes, alpha, you have the order as alpha minus one. So if fractional order goes to one, that's going to be a zeroth order operator, is it?
Uh, Let me think. So, okay, I will try to answer you. But if I'm wrong, maybe Mamikon here can my course on the paper. Maybe Mamikon here can help as well. So yeah, so actually when we do this analysis, we actually specifically try to confine alpha to be between one and two. But I have that for a different reason, for a more physical reason, which I actually have a backup slide I didn't show, but because people also studied Levy work for alpha smaller than one, right? But for if you have alpha smaller than one, then it's even more ill conditioned because the not only the so for alpha smaller than two, as we know the variance of the distribution diverge, but you still have a finite mean, right? Still have a
Yeah,
finite.
that seems fine. But what you have is a divergence of a fractional gradient operator. So so let's say alpha, I assume here is 0 to 1. So at so if alpha is 1, the inside the bracket you have a zeroth order operator.
Yeah.
So
Yeah,
so should
I can only answer it from a more physical perspective. Maybe Mamikon can help with
but in a
physical
physical
perspective. Yeah,
in a
the
physical
physical
pers
perspective is that, I cannot have alpha equal to 1 or smaller than 1 because that will make my average runtime diverge. But the average runtime is something I can measure from the experiments for the bacteria. So I don't want it to diverge. So that's why I constrain it to be larger than 1. Maybe Mamikun can help to answer it mathematically.
So I don't remember all the details myself. This was a few years ago, but I do remember reading, the Clafter papers about the Levy walks, um, and they do break it down into different cases. Um, I think we are restricted to alpha between um, um, alpha greater than 1 here. So I don't think there's a question about that. Is
I
there?
see.
Yeah.
I see. I see. So you're so you're defining fractional. So that gradient operator, you have basically alpha between 1 and 2, not 0 and 1.
Yes.
Okay. Okay. All right. I guess we are almost running out of time. So I'm just gonna ask, are there any more questions or comments? I believe no. So this would be a good point to close this talk here. Thanks,
Okay.
Edmonds, for the very nice talk. It was very nice having you here today.
Yeah. Thank you. Thank you. Yeah.